And we talked about these inflection points a little bit because we had a stationary inflection point with an x cubed graph, and on the last x to the 4 graph, that also had a stationary inflection point. Now, if you take the word stationary out of there and just talk about inflection point, that's just where something changes concavity. So on a graph like a sine or a cos graph, it's changing concavity in lots of places. Here we'd say it's concave down. Here it's concave up. Then it changes back to concave down, and so on and so forth. So we say something is concave up like this if it has that kind of curvature. Okay? So whenever you draw a tangent here, no matter where you draw that tangent, the curve is above those tangent lines. And wherever it's concave down, if you would draw tangents on there, the curve is always below those tangents. Kind of looks like a mustache. Nice. So let's look at this example here. We're going to just describe things as concave up or concave down. We'll use two different colors. And they put the points on there to help you out. So P, Q, and R are inflection points. So things are changing at there. From this point up to P, we will label everything in green as concave, up or down. That is concave up. Okay, you can think of the U in up to help you remember that. You can think of feeling up and smiling, if that helps you. And then in this section, which we better use red because red is a negative color already, from P to Q, that would be concave. Concave down. Now we have an interesting thing here. We have from here to here is concave up. From here to here is concave up. We got an interesting thing right here because the tangent wouldn't exist at that point. There would be no derivative at that. Because no matter, you could put a whole bunch of tangents on that, sort of like a teeter-totter. And then finally here, we have concave down again. So those places where it changes concavity, those are called inflection points. And you can use the second derivative to test for concavity. Okay, so I've got some graphs here. They're not connected to each other, just two different examples. Okay, what I want you to see here, what the second derivative is just the derivative of the first derivative. And a derivative, another way that we talk about derivative is its slope, its rate of change. So anytime we're looking at slopes, we're looking at how things are changing. So in this curve here, which is concave up, if we look at each of our derivatives go from 0.24 to 1.07 to 4.05. Okay? They're increasing. If they're increasing, if a function is increasing, we knew that its derivative was positive. Okay? That's something we had from before. If any function f of x is increasing, then the derivative was greater than 0. That's something we had from before. Now, if our derivative is increasing, then our second derivative would have to be bigger than 0. So if we notice that our derivative is increasing, if we look at these numbers, 0.24, 1.07, 4.05. Even here, as we go from left to right, we're at negative 1.4. Then we go up to 0, then up to 1.63. And you can imagine those tangent lines going along there. They're just going to keep getting steeper and steeper and steeper, and they'll keep increasing. So if our derivatives are increasing, that would have to mean that our second derivative is greater than 0. So one of the things we're going to find is if we want concave up, we really have to think positive. We can even put plus signs for the eyes, because if our second derivative is positive, that will mean that our equation is increasing and our derivative will be greater than 0, and we'll have a concave up. Similarly, if you look at something where it's decreasing, again, we can put the same note that we had from before. If f of x is decreasing, then we knew our derivative was less than 0. So if our derivative is decreasing, then our second derivative would have to be less than 0. So if we look as we're going from left to right, we go from 10 to 1.42 to 0.29 in this case. Those derivatives are decreasing. And so we have concave down as a result. Here we start with a positive slope of 1.6. Here it's at 0. Here it's a negative slope. So your derivatives are decreasing. And that's why we can draw that guy to help us remember. So then this gets us to how you can test for concavity. If you find your second derivative, and you find your second derivative is greater than 0, then it's going to be concave up. If you find your second derivative and it's less than 0, it's going to be concave down. Okay? And wherever it's equal to 0, or wherever it changes from concave up to concave down, which can only happen if it's equal to 0, then we're going to have an inflection point. So very much the same way that we have done so far. You have some function, f of x, right? What did we do when we're sketching graphs? We found the derivative, and then we made our derivative equal to 0. So maybe we had 2 points, found out it was positive, then negative, then positive if it was some cubic function per se. Then what we're going to do now to add to it, we're going to add the second derivative. We're going to figure out what our second derivative is and make it equal to 0. And by doing that, we'll find out an inflection point. And we might find out that it's negative in one part and positive in another part. You can make a little cyclops if that helps. And this could be our graph. So this would be very typical of some kind of x cubed graph. I don't know exactly what that equation would be, but if we think about a typical x cubed graph that looks like this. This point and this point would match up with our maxes and our mins. When we take our second derivative and find out where it's equal to 0, it'll be this point right in between. And you can see the change from this part being concave down to this part being concave up. And that's what that inflection point will find for us. And then you'll have even a nicer way to graph it, because you'll have maxes and mins. You'll know when your graph is increasing and decreasing, and you'll be able to show exactly where it changes its curvature with that inflection point. Okay? There are some cases where getting the second derivative equal to 0 isn't enough to show that it's actually a change in inflection. A very typical example would be to take a function like f of x equals x to the 4. Okay? An x to the 4 graph, when it's just like that, acts very much like a parabola. It's just even flatter than a parabola at 0, 0. Now this is an easy one to do the derivative, right? F prime of x would be 4x cubed. And it's pretty easy to see that at 0 you have a minimum. And it's pretty easy to solve that. If you were to take the second derivative here, well, that's also pretty easy to do. You get 12x squared, and it's pretty easy to see that 0 works there as well. Can you see that? But this is always concave up. So this note is saying it's not enough to show that the second derivative is 0. You must also show that the first derivative does not change sign at that point. So on this one, after our first derivative, if I put in 0, I would notice that it's going down because it's negative to begin with. It's decreasing, and then increasing after. Now, because it's changing points at this, we know that this is a minimum point. And you can never have an inflection point at a minimum point, because it's impossible to change your curvature at a minimum or a maximum. Does that make sense? That there's a minimum, here's a maximum. It's impossible to have your graph turn to a different kind of curvature unless it was a stationary point of inflection. Okay? So just because your second derivative is equal to 0, that's not enough. Okay? But if you have a graph like the x cubed one that we saw before, this is where you have your max and your min. That's where your function's going to change. Here your derivatives are positive, here your derivatives are negative, and then after positive again. Then in this case, this point in between will come up as an inflection point, and it'll change curvature at that point. What this helps in drawing is I actually start when let's say I have a cubic graph where I found these were max and min, and I knew that this was my inflection point. I actually start from my inflection point and draw it, and you'll get a very nice looking cubic graph that way when you're drawing it, because the curvature will flow nicely. Okay, so let's get to some examples.